Hello, this is video number 6 on honors linear algebra and multivariable calculus. So in this video we're going to go over some examples of subspaces. Last time we talked about the subspace criterion, which tells us how to find out whether some subset of Rn is a subspace or not. So what we need to do is to check that 0 vector is in W and W is closed under addition and closed under scalar multiplication. So we're going to go over some examples now. Here's the first example. Span of vectors. Let A be a set of vectors in Rn, and let span of A be the set consisting of all vectors that are linear combinations of some vectors of A. Then span of A is a subspace of Rn. So we're going to go over the solution to this one. So in order to do that, we will use the subspace criterion. Okay, so how do we apply the subspace criterion? We will have to show 0 is in that set. 0 is in the span of A. We know that 0 is a linear combination of basically any set. In particular, 0 is a linear combination of the empty set. So 0 is a linear combination of a list of no elements. This is by definition, if you recall, when we talked about linear combinations, we said if you have the empty set, we consider the linear combination of no vectors as just 0. So this means that 0 is in fact in the span of A. So that's the first step. Next, we'll have to show that in fact span of A is closed under addition and closed under scalar multiplication. So let's take two elements in span of A. So let X and Y be in span of A and C be some scalar. So what does it mean that X is in span of A? It means X is the sum of Ci Vi, I equals 1 to n, and Y is the sum of perhaps the I equals 1 to m for some vectors Vi and Wj inside A. And let me just change that to J. Okay, so that's just by definition of span of A. Now I'll have to take the sum of these two and I'll have to take the scalar multiple of one of them. If I look at X plus Y would be the sum of Ci Vi plus the sum of Dj Wj. This of course is a linear combination of, so this is a linear combination of vectors V1 through Vn and W1 through Wn. So what does that mean? That means that this sum, X plus Y, is in fact in the span of A. If I also rescale one of these, C times X, that would be the sum of CCi Vi, which is of course in the span of A, again by definition, since Vi is in A for every I. And that means this set satisfies the subspace criterion. It contains 0 vector, it's closed under addition and scalar multiplication, therefore it is a subspace. So that was one example of a subspace. Here is the second example, and this is kind of like same example, still along the same line, and this is stated as a definition. So consider you have a matrix that is m by n. You have m rows and n columns. So any matrix with m rows, so this is number of rows and this one is number of columns. So this example is a 3 by 2 matrix, 2 by 3 matrix. It has 2 rows and 3 columns. The row space of A, which is the span of rows of A, is a subspace of Rn. So if you look at rows of A, they would have n entries, and those m rows would give you a subspace of Rn if you look at the span of them. And the columns would give you the column space. So column space and row space are defined as span of columns and span of rows, and they are in different Rn's. One of them is in Rn, the other one is in Rm. Here's an example. Consider the matrix this. Describe the row and column space of the matrix above. So let's work on that. So what is the column space? Column space of this, let me call that A, is span of three vectors. Vectors 1, 0, vector 2, 4, and negative 1, 2. So if you think about this, 1, 0 gives you all of the x comma zeros, and you can create 0 comma 1, and in fact every vector using the other two vector. If you just take one of the other two, you would be able to obtain everything. So if I take a vector x comma y, I can write it down as a linear combination of 1, 0 and negative 1, 2. I want to see if that's possible. So this is the same as saying xy is a minus b and then 2b. So if I take y equals 2b and x equals a minus b, I would be basically done. So a and b can be obtained by b is y over 2 and a is x plus y over 2. So it means every vector xy is in the span of those three vectors 1, 0, negative 1, 2, and the last one, but last one is like not even needed. So this means the column space of A is in fact the entire R2. So that's one thing to keep in mind. The other one is the row space of this. That was a little bit easier, so I did the row space first. The row space is the span of the rows of this matrix. So let me write it down. So the rows are 1, 2, negative 1, 1, 2, negative 1, and 0, 4, 2. I will have to find the span of these two vectors. Yeah, I forgot the span at the beginning. So I need to find the span of these two vectors. So what is the span of these two vectors? It is basically every vector that is a times 1, 2, negative 1 plus b times 0, 4, 2. I want to understand this a little bit better. So this is not the entire R3, but it is a comma 2b plus 2a plus 4b minus a plus 2b. So I'm looking for all x, y, z that x is a, y is 2a plus b plus 4b, and z is negative a plus 2b. So we can find a and b from here. We can say, well, a is x, b is, from the second one we can find b. B is y minus 2a, which is 2x, over 4. And then z is, if I find the relation between these, that would give me negative a minus x plus 2b, which is y minus 2x over 2. This would give me y minus 4x over 2. So it looks like the the row space would give you all of the x comma y minus 4x over 2. So everything of this form can be written as a linear combination of these two vectors, and everything of this as a linear combination of those two vectors is of this form. So the row space of A is the set of all vectors of this form, x comma y comma 4 minus y minus 4x over 2, where x and y are real. So this is the row space of this matrix. Okay, so let me move on to another example. Row space and column space are in fact vector spaces. So why are they vector spaces? If you look at a matrix A, if you look at the matrix A, let's say it's m by n, you have m rows, so A1 through AM, and these A1 through AM are in fact in Rn. So if you look at the row space of A, by definition, row space is just the span of these vectors. And in a previous example, we showed that it is a vector space, so which is a subspace of Rn. And then similarly, if I look at columns, it would be the subspace of Rm. So column space of A is a subspace of Rm. So that completes the proof. I mean, this part is like very similar to the other part. Okay, so now these were some examples about subspaces, very important examples, and we'll come back to these quite a bit. So I will see you in the next video.